Okay, let's continue on with this reaction diagram. Let's talk about C and D. So with C and D, all this is talking about is which axis things are on. So the reaction energy on C is always going to be on the y-axis. Okay, so that's this right here, energy. Okay, and then the reaction progress is going to be the x-axis. So this is just showing the progression of the reaction, how much time it's taking, because remember, time is always on the x-axis. Okay, so now that we have that done, let's go ahead and talk about number 2. So when we're talking about a catalyst affects the activation energy by lowering the activation energy. And when it does this, it affects the reaction rate by increasing the reaction rate. So if we were to draw a little graph again, a catalyst is just going to lower that activation energy, so it's just going to be below the highest point right here. Oops, that was the same color. Didn't mean to do that. Okay, it's going to be below it. So now instead of the activation energy being all the way up here, okay, it's now just right here. That's our new activation energy from having a catalyst. So a catalyst just increases the reaction rate by lowering the activation energy. Okay, let's go ahead and move on. Now we're going to just do some whiteboard things. So if you're at home and you weren't at school today, you can go ahead and pause the video and do this and then come back and check so you can double check everything. Okay, so first thing, potential energy of reactants. That is going to be, sorry, I'm just having difficulties all day long with technology. Sorry. Okay, potential energy of reactants. This is just where the reactants start. Potential energy is just the stored energy. So this is where your reactants are. Notice that it's 30. So this is 30. And it says energy. We're going to assume kilojoules if no units are mentioned. Then the potential energy of the product, again, that's where we're ending, is the products right here. And if we go over to this line, this is at about, this is at about 80 kilojoules. Okay, so those are the answers there. Then we need to go ahead and we need to do the activation energy and the heat change, which we already talked about in the last video. So in this one, we are going to, see what I mean? I'm just having technical difficulties today. I do not know what is happening. Well, I do, but I'm having issues is what's happening. Okay, so to find the activation energy, remember it's the highest point, which is right here, so it's 110, and you're going to subtract it from the starting point, which is going to be where the reactants are. So you're going to subtract that from 30, so we're going to get 80. So the activation energy for this diagram is 80 kilojoules. That's how much energy it took to go from the starting point up to the highest point on the graph. Okay, then for our delta H, on this one, you look at the difference. Remember, delta H is products minus reactants. So your products right here are ending at 80. We're going to subtract that from the reactants, which is 30, and we're going to get 50. So for the delta H, that's 50 kilojoules. So what that is the difference between our reactants and our products. When we have a positive delta H, so this 50 is positive, it means this is an endothermic graph. And you can tell because delta H is positive, you've got an up slope, that's your most dominant slope, is going up, and your products are at a higher energy than your reactants. All right, next one, go ahead and do the potential energy of the products and reactants again. So on this one, our reactants are right here at 90, and our products are right here at 30. Notice you'll always have reactants on the left, products will always be on the right. And so again, 90 for reactant, 30 for products. Our next one is finding the activation energy for this. Sorry, I'm just having major Technology problems. Okay, here we go. Okay, so on this one, activation energy again is the highest point, which on this graph is 120. And we're subtracting it from the starting point, the reactants. So we get 30 kilojoules for our activation energy. For our delta H, again, it's the products on this part, 30, minus the reactants, which is 90. So 30 minus 90 is a negative 60. Okay, that's your delta H. That's supposed to be a triangle. And that negative sign is very, very important. That tells us that this graph is exothermic. And so make sure you are very, very careful and you keep your signs correctly. Okay, now we're going to do some things on this reaction page. This is actually page 11, not page 8. So go ahead and go there, and we're going to do some of these together. We did a lot of this in class with partners, and so sorry because you're at home, you don't have that same partnership. But we're going to go ahead and we're going to look at this. So really quickly, we're going to do 1 and 2, and then 3, 4, and 5 I'm going to have you do on your own. But this is just like what we did just barely with our whiteboards. Okay, so number 1, in terms of energy change, what is the difference between endothermic and exothermic? So endothermic, remember, absorbs energy. Exothermic releases energy. On A, the answer is endo, because it's a positive delta H. On B, let's take a look at this one. If I write out a reaction and I have, let's say I have A plus B, I'm going to add heat as the reactant, and then I get AB as our product. When heat is a reactant, this is an endothermic reaction because you are taking in the heat. Okay, C, delta negative, that's going to be exothermic. And if we change this reaction right here, and we say A plus B, our product's AB, and then we have heat on the product side. When we have heat on this product side, it means that it's exothermic because the heat is being released. So just look at placement there. Okay, let's look at number 2. And number 2, the first thing I want you to do is draw 2 arrows, one from the solid to the gas and one from the gas to the solid. So the first question, well, not the first, but number 2, it says when going from a solid to a liquid to a gas, so a solid to a liquid to a gas, this right here, energy is blank. Okay, so think about what do you have to do to go from a solid to a gas? You've got to absorb energy. So this is absorb. And this is an endothermic reaction. So you can go ahead and write endothermic on top of that arrow. And then the second part of the question says when going from a gas to a liquid, so that's this direction, energy is blank. Okay, so to go from a gas, a less organized, to a more organized, you have to have heat released. So that answer is released. And this is showing an exothermic reaction. Okay, now let's go to the very bottom, number 6 and number 7. Okay. On here, we're drawing a graph. So what we're trying to do is draw a graph like this. Okay, we want to see the reaction progress. In order to do this, we have to use our equations that we just learned, our activation energy equation and our delta H equation. Okay, so I'm going to go ahead and write these up here. E of A equals, remember, equals the highest point subtracted by the starting point. And then our delta H, remember, is our products minus our reactants. Okay, so the first thing we want to do is we want to go ahead and we want to do this graph, kind of label it. And I apologize, my writing pen isn't working on this, and so I have to use my finger, and I can't make things small. So on here, just label go 0, and then maybe like every increment go up to 10, go up to 120, which is going to be up here. Okay, and then I'm going to have like 20 here. Okay. So the first thing is we've got potential energy of reactants at 20. So I'm going to draw a little line on 20. Okay. And that's where our reactants are starting. Okay. Then we've got a delta H of 50. So I'm going to go ahead and write that over here. We're going to do some math. And I have an activation energy of 100. And again, our starting point is 20. That's our reactants. So I'm going to go ahead and put those there. Now notice on these equations, I've got 2 out of the 3 variables. So now we're just going to go ahead and plug in variables. We're going to find the highest point. So we're going to say x equals a negative 20. X minus 20 equals 100. And so what do we have to do? We have to add 20 to both sides to get the x by itself. So now x is going to equal 120. This is our highest point. So I'm going to put a line in the middle. This is where it's going to go. The graph's going to go to the highest point, if I can get this to work, right there. Okay, third time's a charm. Okay, then we're going to do our delta H. So our delta H, we're trying to find our product, so we're going to make that the x. So again, x minus 20 equals 50. We add 20 to both sides, and that's going to give us 70. And that P stands for our product. So I'm going to go ahead and do like a little line. I know this isn't perfect, but my fingers are so big. 20, 30, 40, 50, 60, 70, about right here-ish. Okay, so now we've got reactants right here. We've got products right there. And this high spot is like the highest point we have on the graph. So now we're just going to draw a line. And a curved line. So I'm going to do the best I can. I'm going to start here. I'm going to go up, and then I'm going to go down. Okay? So this is what our graph looks like. So from this graph, we can now tell if the reaction is endo or exothermic. So first of all, just from our delta H, the fact that our delta H is positive right there, that means this is endothermic. But we can also tell it's endothermic because our products are higher than our reactants. And also, if you look at the fact that the line that's going up the highest right here, that's showing an increase in heat, which is also an endothermic quality. Okay, go ahead and do 3, 4, and 5 on your own. I will put up a page so you can check those. And then tomorrow we're going to do more practice on what we just did on number 6 on drawing these graphs. Okay, thanks, and I hope you're having a great day. Bye.